Hello everyone, welcome. This is a class ECE451 Control Engineering. Last time we introduced the rule lockers, right? Rule lockers, we know how to give a rule lockers by MATLAB. We also study some basic properties of the rule lockers. Today we keep working on these. Okay, let me. It's a ECE451. This is a lecture for the 5th week, the Wednesday's class, right? 5 days Wednesday's class. Okay, so we'll keep working on the rule lockers. We consider a feedback system like this. And here's a K. Here's a K, plus and a minus. This is the input R. This output Y. All right. Then we have T of S, the transfer function of the whole system, which is Y over R. Right. This one equal to G of S over 1 plus K times G of S. And we can also write it as a fraction of polynomials. Here this is a fraction of fractions, right? G is a fraction, so this is fraction of fraction. And we can write it as a polynomial. Suppose this is A of S plus K times B of S. Here's A of S. If G equal to A of S over B of S. Am I good? Oh, sorry. This should be A over B, then this is A. This is B. Okay. Yeah, like this, right? B, K times A, and the B move to this way. Okay. So we have the system transfer function looks like this. Okay, then what is the rule lockers? Orbit of poles of T of S when K change, and here we can when K change. Yeah, we can, in most cases, we can suppose K is positive, but sometimes you still need a negative, right? In most cases, K is positive. So here, when K is changing, K changes. Yeah. And we already know something about it. K equal to 0. Then the poles of T of S equal to poles of G of S. Right. Yeah, use a set. And K is infinite. Then poles of T of S is the same as zeros of G of S. Right? Yeah. So we can think of this, the rule lockers is a curve start from poles of G of S and ended at zeros of G of S. Right? Okay. And then we have something. What else do we have? I can't remember the order last time I introduced. I just write here what I talk about, right? 1, 2, 3. We consider the breakpoint. 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 Breakpoint that is we want the b s plus k a of s equal to 0, as well as the derivative of b plus k derivative of a equal to 0. And from here is d over ds, right? You take derivative according to s. So from the first one you can get second one. And solve these two. Solve these two, we can have the breakpoint. Breakpoint means point with multiple poles. Okay. Yeah, of course it is poles. We are talking about poles of t. Poles of t. Okay. The breakpoint. And we also have the marginal point. Right? The marginal point we also need to solve. We want the denominator equal to 0, but this time the pole, the s, should be a imaginary number, pure imaginary number, just j times w. So we want the b of j omega, b the jw, j omega, alright, plus k a of j omega. This is 0. We solve this, we can have the marginal point. Right? And fifth, we have so how many the locus, right? There are some branches, several curves. So how many curves do we have? We say the number of all the locus losses. They are the maximum of number of poles of G and number of zeros of G. Yeah, the larger one of these two numbers. And then we consider the number of loci go to or from infinite. This number equal to okay, I give a notation I call these as m. I denote these as n. Right? We have m poles and n zeros of that G. Right? Then here will be m minus n, take absolute value. Alright. Also we call this is we know they are asymptoters, right? Asymptoters. And the asymptoters, for asymptoters we have some property, two properties basically. One is all the asymptoters, you can consider they start from center point, and the second is all the asymptoters will separate the whole space into several pieces, right? Several pieces. So we have these. First one, how to say this, or asymptoters start from center point. I say that is a center. I just write center. Okay, center. It will be a real number. It is a summation of all the poles minus summation of all the zeros divided by this number. How many branches go to infinity? Right? It's m minus n, like this. Pi, they are poles of G of S and zi, they are zeros of G of S. Right, this is the center. This is center. Right, center. And it will start from the center. Like this, right? Start from the center. And the second, the direction of, this is a, let's say the 5.1. This is 5.2. Alright, this is 5.1, 5.2. The direction of the asymptoter. Totally is a 2 pi, right? Totally around is 2 pi. So it is a 2 pi over n. 2 pi over n. So it will look like this. So here is 2 pi over n. 2 pi over n. And the first one here is a 2 pi over n and 2 pi, a half of it. So it's a pi over n. Branch 1, branch 2, branch 3, and so on. And the last one here, the last one. Totally we have, this is a m minus n's, right? Here is another pi over n, right? So every 2 pi over n angle, we have a branch. Every 2 pi over n angle, we have a branch, like this. We can also write as a formula. There will be pi over n plus k times 2 pi over n, where n is just that m minus n, and k will equal to 0. Right? First one 0, then 1, 2. Totally we have n, so it's n minus 1. Okay, so this one, the directions, right, are these angles. All right. Last time, let me see. We have discussed this 5 topic, right? Maybe at that time I gave one more, but now I combine some together. Yeah, so totally 5, and the 5th contain these 2. All right. Okay. Today we consider some more things. Okay, I see this is the 6th. All right. The 6th one, if S equal to S0 is a point at the rule locus, then S0 is a pole of T of S when K equal to, right? This one is it's depending on K. Different K, you can have different T of S. And for certain K, its pole will be this S0. Then what is that K? That K is negative 1 over G of S. Right? Make sense? Because 1 plus this one, 1 plus k g of S0 equal to 0, right? It is a pole, so we have this one. Then we have k g of S0 equal to negative 1. And then we have k, right? K is negative 1 over g of S0. Right? So we have k. That means you check the any point, you can pick any point from the rule locus, and then what is the k related? You just calculate this one. You have k. All right. And 7 things about the direction, the angle, direction of the lossy rule locus, about the rule locus, direction of the angles. Angle. We can think like, for example, we consider g of s, which is 1 over s squared minus 2s plus 10. This is g of s. We have s plus 2, okay, like this. Then we know the PZ map of g of s. Well, it looks like we have 0 at negative 2. And s squared minus 2s plus 10 equal to 0 give us s minus 1 squared plus 9 equal to 0. So s equal to 1 plus or minus square root of 3 times j. So we have here, this is 1, this is the square root of 3 here, right? This is a cross, this is a pole, this is another. Oh no, sorry, square, just 3, It's 9. 9 is a square root of 9, not 3. Yeah, and you remove the square root. Okay, it's just 3. It's a negative 3. It's here. Alright, we have PZ map looks like this. Okay, then we know how many branches of these locus, root locus. We need to have 2 branches, right? 2 branches, because I have 2 poles, 1 zeros. Then the larger number is 2 poles, so we have 2 branches, and they will start from the poles, and one branch will go to 2, the other will go to infinite, and the infinite one we use these. Totally we have should be pi over. Now we have 2 branches, right? Oh, we have only one branch. One branch go 1 and same totals, right? We have 2 poles, 1 zeros. So we only have 1 branch will go to infinite. 1 branch go to infinite, so this angle will be pi over 1. So this angle actually is 180 degree, just 1 branch, right? So we have the root locus looks like start from here, and 1 go to infinite, right? 1 asymptotes, 1 asymptotes, right? And we have 0 here. Okay, now you know. Oh, we have another one. I will say symmetrically. Did I put it here? Breakpoint. Okay, yeah, I said in last time we have more features. Okay, I will say here. This is 6. I say this is 6 to 5. All right. Yeah, between 6 and the 5th, we have one more thing. Symmetrically. See, symmetric according to the real axis. Right, we have this. Okay, so if this go this way, this will go this way. And okay, you will think if this one go to here, go to this one, then this path will go to here. But then no way to go to infinite because this part is already occupied by something else. Okay, so only way is this one go to here somewhere, go back to this 0, right? From infinite to 0, and another branch symmetrically go to the same place, and okay, from the real axis go to infinite, negative infinite, right? So the whole curve looks like this, right? Whole curve looks like this. But like here, maybe they go this way, maybe they go this way, right? I don't know. So I want more description about this direction. The curve will go this way, or this way, right? We need to know that. The direction. What is the direction? Then firstly we consider the direction at here. This is a point like start point. The root locus start from pole of G of S. Start from this cross and will end at 0 of G of S. This place K is 0, is start point, and this place K is infinite. Right? 0, then some K larger than 0, finally go to infinite. This is K. Along the direction of K, right? We have start point and end point. Now we want to know the direction here. We call this is a departure direction, right? Departure direction. And here is a arrive direction. So we need, first of all, we need these two directions. Right? For the asymptotes, no problem. It will go to infinite, right? Like here, it's go to infinite. Yeah. Of course, depending on if we have like 2 zeros, 1 cross, then this from infinity will go back to the cross. That will be the direction will go back from infinite to that poles, right? Now is from poles to infinite, so the direction is like this. All right. Before we start to discuss the direction, we need to study something related with the angles and directions of vectors in the complex plane. Right? This is complex plane, the S plane. You can think this is a kind of some notes on directions of I would say vector on complex plane, complex space of complex numbers, right? Space of complex numbers. Then we have the real axis, we have the imaginary axis, and suppose we have a point. Here's a C, a complex number. C is A plus BJ, right? Then, okay, we can consider C as a vector. C is a vector. Start from original point and ended at this point, right? So C, you can also consider it as a vector. And here you have angle theta. And here will be the length, the rho, right? The length of the vector. Okay, now the relation is like this. C is a complex number. A, the real part of C, and B, the imaginary part of C. And C, it is angle of C, and we can have cosine theta equal to A is the real part, right? A is the real part, and B is the imaginary part. So it's A over rho. This is cosine theta, right? A over rho is cosine theta. This is the definition of the cosine, right? Cosine. And the rho, this is the length of this vector or this distance, right? Length of C, and we denote it as this one. Theta is a angle C is theta. We use this notation, angle. And this one we have rho equal to A squared plus B squared and square root. And rho is denoted as like this. This one, the rho. This is notation angle theta. This is notation magnitude or the length of C is rho. Okay, the magnitude, right? The magnitude of C, right? Magnitude of C. All right, and we have another way to write it. That is is given by Euler. Euler formula. Rho times e to the jc equal to a plus bj, where e to the j set, that means cosine set plus j sine set. Right. We have this. So basically, is this one. In this one, then you just plug in, right? A is what? A is rho times cosine set. And what is b? B is rho times sine set, right? B is rho times sine set. So you just plug in, then you can have a plus bj is rho times cosine set plus j sine set. Okay, so we have this one. Now we can describe this direction by this angle, right? This angle gives us a direction from original point to this C. Okay. So this is the angle, give us a notation about this direction. Alright, now we consider we have two complex number. Then we can consider one is C1, A1 plus B1J, and C2 is A2 plus B2J. Then we have C1 minus C2. Right, okay, what is C1 minus C2? Okay, this is C1. This is C2. Then what is C1 minus C2? In real part, so it will be C1's real part minus C2's real part. So it's A1 minus A2, right? Here's A1. Here's A2. A1 minus A2. A1 minus A2. So it is this distance, right? This distance. And this side, this is a B2. This is B1. So imagine part you also need B1 minus B2. B1 minus B2. So we have this part. But this is negative value, right? B1 minus B2. B1 is smaller. So this I put a negative here. Or you can put the arrow. This is a positive, right? Like this way. Okay, so you see, this is a direction, and you connect these two, right? So from here to here, this one actually in the imaginary axis, it goes from B2 to B1, right? B2 to B1, and in real axis, it goes from A1 to A2 to A1. So we have like a vector, an arrow from C2 to C1, and this is just C1 minus C2. This is C1 minus C2 equal to A1 minus A2 plus J B1 minus B2, right? It's just C1 minus C2 is here. Oh, you can think, yeah, the complex number should be, this is a complex number, right? It will start from here, actually to Oh, I don't have enough space. Okay, I give the graph again, like this. I have C2, I have C1, C1, and this arrow actually is same with this. So this is a C1 minus C2, C1 minus C2, and they are same thing, right? You just move these parallelly from here to here, so these two are same. All right, yeah. Like this. All right. So the direction of C1 minus C2, because this is direction, it is from C2 to C1, right? From C2 to C1. This is the direction, and we can have an angle to describe this direction. This is angle of C1 minus C2, or here, angle of C1 minus C2, right? This is the complex number C1 minus C2, and its angle is this one, angle of C1 minus C2, and same angle with this, same angle with this. So this is the angle of C1 minus C2. Right. Okay, so this is for the subject, and okay, you can consider another way. We can consider another side, another direction, C2 minus C1. These give us the direction of direction from C1 to C2. Okay. And you same, like this is a C2, this is a C1, then C1 minus C2 will be this direction. Actually it will be here. This is a C2 minus C1. C2 minus C1 is this direction. Alright. Yeah. So we can use the angle of these to give the direction from C1 to C2. That is the angle of C2 minus C1. This gives us the direction. And this is also from C2 to C1, we can, that is the angle of C1 minus C2. Right? C1 minus C2, the angle of this. Right. Okay, so in the complex space, in the complex plane, we can use the angle of a complex number to give the direction of single complex number. We can also use the angle of this subjected number to give the direction between two complex numbers. Right? We use this angle. This angle describes the direction from C2 to C1, and this angle describes the direction from C1 to C2. Right? Okay. This is one thing. And the second thing about multiplication and division. Here we consider the minus, right? Subtract. Yeah. We can also consider the C1 times C2. Now consider multiplication. C1 times C2. What is the angle of this? What is this? Okay, we just use the Euler formula, Euler way to represent it. C1 is rho 1 times e to the j theta 1. And C2 is rho 2 times e to the j theta 2. Alright, now things become simple. It is just rho 1 times rho 2 and e to the j theta 1 plus theta 2. So angle of C1 times C2 equal to C1 theta 1 plus theta 2. And actually theta 1 is the angle of C1 and theta 2 is the angle of C2. Okay, it's a good feature, right? When we perform multiplication of two complex numbers, then the result complex number will have the angle as a summation of the previous two numbers, right? Yeah, you have two complex numbers, each has a direction, each has an angle. Then you do summation. That will be the angle of the C1 times C2. Right? And of course, at the same time, you can also have the value of the magnitude. We know the magnitude of C1 times C2 will equal to rho 1 times rho 2, right? Which is a magnitude of C1 times magnitude of C2. Yeah, right. So this is for the multiplication. And then similar thing, we can have the when we do the C1 over C2, we perform the we divided one by another. We have C1 over C2, C1 divided by C2. That will be rho 1 e to the j theta 1 divided by rho 2 e to the j theta 2. Alright, this is what? This is rho 1 over rho 2, right? Rho 1 over rho 2 times e to the j theta 1 minus theta 2. Okay, so this is the angle, right? This is angle, this is magnitude. So we have the magnitude of C1 over C2 is rho 1 over rho 2, and for the direction we have the angle of C1 over C2 equal to theta 1 minus theta 2, theta 1 minus theta 2. And I use a notation. This is the magnitude of C1 over magnitude of C2. And the angle here is the angle of C1 minus angle of C2. Okay, so we have these two features. When we have multiplication, the angle, the direction, the angle, you do summation. When you have the division, the angle, you do subtract, the minus. Right? Okay, now we have enough preparation for the angle of root locus. Now look at the root locus. If s equal to s0 is a point in the root locus. We have 1 plus k g of s0 equal to 0, right? For some k, for some k value, right? We have this one. And what is g? Okay, here we need an assumption for simplify. We suppose g of s equal to s minus the first 0 times s minus the second 0 until s minus how many zeros do we have? I use the notation for zeros. I use n for zeros, right? N for zeros, and m for poles, right? N for zeros, m for poles. Okay, then I use the same notation. This is n for zeros, and for poles, s minus pole 1, s minus pole 2, s minus pole m, a denominator. And here we have a coefficient a, and we suppose a positive. A is positive. Okay, we use this assumption, or even suppose A is 1. A is 1. Then we have 1 plus K times A times S minus Z0 S minus Z1 Z2 sorry S minus Zn over S minus P1 S minus P2 until S minus Pm. We have this equal to 0. Okay, now here's some positive K. Suppose we consider positive K. Alright, positive sign. So we have this. Then we can have, let me see, I move 1 to the other side, will be negative K, negative 1, and Ka is also to that side. So we have S minus Z1 times S minus Z2 S minus Zn, all the zeros, and the poles S minus pole 1 S minus pole 2 S minus pole m are equal to negative 1 over Ka. Right? So we have this one. And by this assumption, this side will be negative value. For positive K, this is negative value. If K is negative, this will be a positive value. Right? For negative K, this is negative value. For positive K, this is a negative value. For negative K, this is a positive value. Right? So we have this. Then, how about the angle? So I will say the angle of S minus Z1 plus until the angle of S minus Zn, right? Here's multiplication, right? So this is the angle due to summation, and you divide it by them. You need to subtract angle of S minus P1 minus angle of S minus Pm. This side, this is the angle of this side, equal to that side is angle of negative 1 over Ka. Now we have this. We call this the formula 1. Okay, we will use this formula to determine the direction for the when the locus start from that crosses. Right? We call it departure. Okay. The direction of locus departure from pole of G of S. Suppose this pole is P. Now I just suppose this is P1, okay, P1, and suppose P1 equal to P2 equal to PQ. That means this pole, P1 is a pole with other multiple, it's a multiple Q. Yeah, suppose Q, and all the rest PQ plus 1 until P, the last one Pm, they do not equal to P1. Right? We just suppose the first all the same one, P1 to PQ are all the same one. And then the others are different. And suppose like this case. Okay, then the direction. How to determine the direction? You look at here. Suppose we have some zeros, 0, 1, 0 until 0n, and some poles. Okay, this is the pole we have discussed. This is pole 1. And we have some rest, pole Q plus 1 until pole M. Okay. And what is the direction here? So this one according to K equal to 0, right? And when K increase, after a while we'll go to somewhere here. Suppose this is S0. K equal to 0 plus some delta K is larger than 0. So this is the direction. This is the direction, departure direction. This is departure direction. So the departure direction, okay, we'll call this the direction of the departure. That is the angle. We use the angle to describe it. That angle, it is just angle from P1 to S0, right? P1 to S0. What is that? That is S0, one minus another one, right? We have this. We want P1 like here, from C2 to C1 is C1 minus C2. So it's from this one to this one. The direction is from this one to this one. So this we will consider the angle of S0 minus P1. Consider this, right? This one. This one give us the direction. This one give us the direction. This one gives the direction. Right. This one gives the direction. So direction from P1 to S0. It is just the angle of the S0 minus P1. Alright, now we apply the equation 1. Equation 1 is here. Right. Equation 1 is here. This S, actually S could be any S0, is a point in the rule locus, right? Is a point in the rule locus. So let me see. It's here, right? S0 is here. S0. Now we apply these. We have by equation 1 we have angle S0 minus Z1 plus until S0 minus Zn and minus angle of S0 minus P1. Okay, I write the same thing here, minus P2 until minus S0 minus PQ. Actually P1 to PQ they are same, and the rest terms, the P are different. It's PQ plus 1. S0 minus PM. This will equal to the angle of this. Angle of this. And now, you see, this case start from 0 and increase to some delta K positive. So this K is positive now. K is positive. Right? K is positive. This is the angle of -1 over delta K times A, which is positive. So this is negative value. That will be the angle is pi, right? Angle is pi. Negative value has angle pi. Right? Angle is pi, or negative pi. If you want to describe the angle, use another direction, negative pi. But same. We think 2 pi is just 0, right? 2 pi is 0. So we have this. Do I need this? Okay, I leave that. Right, we have this. And look at here. Right, this is the angle. S0 minus Z1. S0 minus Z1. Then we consider this is the direction from Z1 to S0, and the angle is here. Angle is here. The angle is here. I use a notation. This is a phi 1, like phi 1, or this divided by phi. Oh, I'm sorry. Yeah, the phi 1. Actually, phi 1 is what? You can see these. This is Z1 to P1. This is also phi 1. We think they are similar thing, very close, because this is a very small number, small distance, right? Delta K is small. Delta K is small. It's a small number. So this one, we can think it is just S0 minus P minus Z1. Not S0, sorry. S0 I can replace by P1. So this is an angle P1 minus Z1. So I can replace S0 by P1. The difference between these two angles, you can think is nothing different, because this is very small. This is very small. Make sense? Yeah. And similar for like a P. I use these to illustrate. So we have this angle and this angle. I denote as phi 1. Actually, I have two phi 1. They are very close. We can think they are same. Alright, they are same. Okay, so I replace these zeros by P1. Right? This is P1. Zeros should be zeros, right? I replace by P1. I get a different angle, but that different angle only have very tiny arrows, so we can think they are same. So this one, all the rest we replace by this one. But this part we cannot replace it, because if you replace S0 by P, this should be 0. You have nothing. I just keep them. I keep them. Okay. What I will do, S0 replaced by P1, right? By P1. So summation until summation angle S0 replaced by P1 minus Zn, and minus all this angle we have n of it, q of it, right? Totally we have q of this angle. I won't change this. I need to keep this, and then minus all the rest. They are angle of P1 minus PQ plus 1 minus P1 minus PQ plus 1 PM. That's why it's PM equal to this side is pi. Almost done. Almost done. I have notation. I use that as phi. This is also, this is ver phi. This is phi, right? So I have angle phi 1 plus ver phi 1 angle ver phi 2 until angle ver phi n minus q. Okay, this is the direction. This is the angle of the we give the direction, the departure direction, right? Yeah. Okay, I still keep this. And minus there this phi, this is ver phi, this is phi q plus 1 minus phi m equal to pi. No, I don't need this. Equal to pi. So q times this angle I write as a c departure of, just of 1. I see 1, from the first pole. The departure angle from the first pole times q, or equal to this one minus this to that side. So this one minus pi. So this is I write this summation of those angle phi I and minus summation, this is phi, this is phi, angle of phi I. Okay, here's we want a pole do not equal to pole 1. All the poles do not equal to pole 1. We have this angle. Here's all zeros. And minus pi. You said plus pi is the same thing, right? 2 pi is the same as 0. Okay, so we have this. And if you, we have more 2k pi, n in k, n in k. Okay, so we have this one. And then you just divide it, right? So departure from the first pole, the direction of the rule locus departure from the first pole, this angle equal to summation of angle phi I minus summation of angle phi I and minus pi plus 2k pi over q and n in k. Okay, here is also the reason why I keep this term, right? If you just look at this angle, nothing different, right? You plus 2k pi, same thing. But when you divide by q, there will be different. Never be different, right? This one, plus 2 pi divided by q and plus 4 pi divided by q might be different because they divide by 2. After divided, this number is not 2 pi, not 2 pi, right? Not 2 pi times of 2 pi. Yeah. Okay. So this gives us the departure direction from pole 1. Departure from pole 1. Yeah. And similar, we can do similar thing. Similar, we have the set arrive 0, like suppose 0, 1, or equal to, okay, it's just negative 1, negative, or is angle of phi I plus angle of this phi I, and here it doesn't matter, minus pi or plus pi or whatever. I still use the same thing, right? This is minus and plus pi and 2k pi over q for n in k. For n in k. Suppose the 0 z1 has multiple q. Yeah, that one is all multiple q. Yeah. And this is a departure direction. A direction from pole P1, and this is arrival direction from 2, it's 2, 0, z1. Alright. Yeah, actually they can work for any pole, any 0. Yeah, I just writing this way. When you consider this pole, you think this pole is pole 1. You consider another pole, then you reorder them, you think, okay, you still consider pole 1, right? So you can just use this formula for all the poles. Alright, now we can study the example. We just we go back to the example, we can know the direction. Example. That one, right? We have these. We have right? It will be a curve looks like this, right? Okay, what is direction here? You can see you need consider all the direction. This direction, this is a verify 1. We only have 1. And this direction, this is a phi 1. We only have one phi. One of this is verify I. This is phi I. We only have this. And this multiple is 1. Multiple 1, right? Root this is pole. Multiple q equal to 1. Okay, then we have the direction, the departure direction equal to this angle. I don't know what it is. I just verify. Okay, verify. Only one verify. Divided by this phi is 90 degrees. It's pi over 2, right? And minus pi plus 2k pi and divide by 1. Q is 1. So here 2k pi nothing special, right? Give us no more angle, so we don't need it. So I just multiply is good. Minus. Okay, so what is this angle? What is phi? I don't know what is phi. Okay, just imagine this is a okay, like this. Phi is this, right? Phi is this. This is a phi. And minus, this is a phi minus pi over 2. Okay, minus pi over 2. And then another pi. Always go to here. The minus more pi, right? Minus more pi. So here this is phi minus pi over 2 and minus more pi. So actually you can say this is a 90 degree like this, right? So from here by 90 degree you get it, right? So here is this one by 90 degree is this one, this direction. All right. Oh, sorry. Okay. Alright, see this one. So the direction is here. So you just from this 0 connect it to this cross and then turn 90 degree. This is this direction, the anti-clockwise. They go to here, this direction. So the curve, the locus start from here, leave this departure from this cross in this direction. Yeah. And similar, you can, if you check this, you will see the direction will be here. It also connect, and here's a 90 degree. Yes, so this direction. Then you can have more description. Right? You know how the curves start. The direction is here. And arrive direction. Okay, we need to calculate the theta for the arrival, right? Arrival. This one is arrival direction. We only have one, right? It is that's formula here. It will be negative all these angle verify and all these phi to summation and plus pi plus 2k pi over q. And now q is also 1, right? Q is also 1. This is 1, so we don't need this. And this 2 actually no term like this, right? Because we consider this point no actual more zeros, so we do not have this, and no terms like this. We only have these 2. So have 0 cross here, the angle, this is the angle, right? And cross here, angle is here. So this is a phi 1, this is a phi 2. So equal to just phi 1 plus phi 2 and plus pi over 1. Right? That's it. That's it. And what is phi 1 plus phi 2? Phi 1 plus pi 2. Phi 2 is just this direction, right? Do summation. So it is 2 pi. It is 2 pi. 2 pi plus pi, that is just pi. So this direction is just this one. Alright, we know the curves go into this 0 by this direction, right? Direction is pi. Direction is pi. Alright. Okay. This is the example. And we can consider this is a case we only have 1, right? We'll have all of these, the multiple is 1. If we have multiple 2 or 3, what will happen? Then you need more directions, right? For example, we just use this one, but we use square of it. Yeah, I use MATLAB to do it. You can see. Let's go to MATLAB. I open here. Okay. Here's a file. So I let s equal to transfer function of just s. So this gives us s as a variable. Then we can use it. I have g equal to s plus 2 over s squared minus 2 times s and plus 10. Right, this is g. This is g. Then we can run the locus figure 1. I have locus g. Right. And figure 2, I use 2 figures. This is locus g times g. G times g. What's the difference? All the zeros and the poles in this g times g, they have multiple 2, right? They have multiple 2. The same zeros and the poles with g, but multiple is double. Okay, then let's run it. Phi. Okay, you need to select the direction and then save it. Save it. I go to desktop. It's 451 for the code. Do I have any? Okay, I need a new folder for the. Yeah, just put it here. This is a locus, right? Direction of locus. Okay, like this. See. All right. Coming soon. It's this one. Okay, you see. This is just for G. Figure 1 is just G. So we have this pole, then the direction here is you connect from 0 to this cross. You have a direction, and the 90 degree, you get this direction. And this side is symmetrically. And this direction to arrive this 0, we know it is a 1. Its angle is pi, right? It's a 180 degree. So okay, it's good. And this one, we double, right? We double it. What is it? Sorry, what happened? I click something. No. This one is double. Double. What I mean double? We go back to the. Example. we use same G, right? We have an example continuous. We consider root locus of G times G. Then we have two cross here, and two zeros here, right? Then what is the angle this way? For this one, departure, for this departure, say departure 1, I need times 2 because the multiple 2. Then equal to, here's a 90 degree and another 90 degree, right? We have two 90 degrees. So 2 of 90 degree, and here's a, I say this is a theta 1, verify 1. Also, I need a 2 verify 1. Which is positive, which is negative. The formula, can't remember. The formula is verify. Okay, departure is verify in front, positive, and phi is negative. Okay, so verify is positive, this is negative, and plus a pi, and plus 2k pi, right, like this. So we can have the departure direction for the departure, the first one will be divide by 2, right? Divide by 2. So this one is a negative pi over 2 plus verify 1 and plus pi over 2 and plus k pi, right? K pi. Okay, these two cancel, so it is just verify 1 plus k pi, right? Verify 1 in this direction, so it is this direction and plus k pi plus pi, another more pi, right? So basically two direction. All right, the departure here, we will have two from this cross. We have two branch start from this direction, this point, this cross, this pole. One is this direction, the other is that direction, right? Two directions, and this is what happened here. Move it. Is here. I can change the axis. I give it axis. Figure 2. Axis. So this is to 4. That is 30. I use the same. 10. It was 10. 10. So it's a okay. Just negative 1, 1, negative 1, 1 times 10. Is 10 enough? Yeah, so if not, it doesn't work, I can change that 10 to different value. Alright. Okay, look like this. Yeah. This looks more clearly, right? So at this cross, we have two directions. One direction, both directions just connect this circle and this cross. But one is go ahead, one is go backward, right? Two directions. One is blue curve, one is red curve, right? Two directions. And this side will be symmetrically. This one will be symmetrically, like this way. And here for the cross, for the zero, we go to here. For the 0, I still have two zeros here, two cross here, two cross here. Then the arrival direction, only one actually. Two of these were equal to, okay, I need this angle. Okay, I write this way. And this angle, I say this is R. This is phi 1, right? Phi. This is phi 1, and this will be negative phi 1, right? Opposite direction. Actually, this is a negative angle. This is a positive angle. They are opposite. So this is phi 1. This is phi 2. Negative phi 1. Negative phi 1. So I have 2 of phi 1 plus 2 of negative phi 1. I have these. These are the summation of phi's. These are summation of phi I. Summation of phi I. Then the formula The arrival is here, right? Arrival is a var phi I need a negative, phi I need a positive. No var phi actually. Yeah, phi is positive, and minus summation of var phi. This is 0. This is 0, and plus pi plus 2k pi. So you see this cancel. So we have 2 of set arrive. It is just 2k plus 2k pi plus pi, and divided we have arrival or equal to k pi plus pi over 2. Okay, it's 90 degree, right? This is pi over 2 and plus pi and plus pi, so we have these two direction. Alright, so these two direction. Right. Okay, that's in the graph. You see here the red branch going up 50 degree, 90 degree, and here's also negative side 90 degree, right? The curve, the light curve one, the light blue curve. You can make it large. You see? Yeah. So here actually the direction is well, this is approximate in my lab. Should be straight up and straight going down, two directions. Right? Okay. So this is a departure direction. All right. Okay. That's all for today. See you next time. All right. A little bit more.